In this lab, we worked with constant acceleration. We saw how a card accelerated phi away with constant acceleration. Here are just some of our parameters and the theoretical acceleration formula we will be seeing. Just to answer these two questions, it is partially negligible because they are small and they do exist, but really it doesn't significantly affect the outcome of our answers. So we treat it as negligible just to focus on Newton's second law. This study has an experiment that examined dynamics of a car-pulley mass system on a frictionless track. It used Newton's second law and it assumed that friction between cart and the track is negligible. However, the results didn't necessarily support the theoretical predictions, and it noted that any discrepancies was partially due to friction. An elevator involves a pulley and motor system similar to our cart and pulley. Those designing elevators must keep in mind constant acceleration and friction.
The materials that we use for the Pascal/Capstone application software. This application software was used to generate the graph that will be presented and displayed later on in this video. We used a triple beam weight scale, and this was to measure the weight of our mass. We used the glider, which was attached to the weight and is also used in the air track. The air track was used to make the motion of the graph. We used the Passport motion sensor, and this was to sense the motion as it came in and away from the sensor. We also used a lab notebook and laptop for observations.
For the procedure before starting any trials, we first measured the cart and the glider attached to the cart using the triple beam weight scale in order to be able to properly calculate acceleration and the velocity values. After weighing the cart and the glider, we turned on the air track, passport sensor, and the capstone system before beginning the trial. This trial consists simply of pushing the car, allowing the weight to bring it back before the string end of the air track pushes the cart away again and the weight brings it back, and so on and so forth. This trial was done only once to get the necessary position, velocity, and acceleration graphs to calculate later on.
To start off with this procedure, first we calculated our theoretical acceleration. With this lab, using Newton's law, we were trying to see if the theoretical value of the acceleration would be able to show us the accuracy of actual measurements from the experiment that was done using the actual glide and hook. The theoretical value is idling and it doesn't consider the friction or the air resistance. So for the theoretical acceleration, we use the formula A equals mw times gravity over mw plus mc. So for following that equation, as gravity is moving, as the glide accelerates towards the sensor, it is negative, so negative 9.8. And as it moves away from the sensor, it's positive 9.8. So our glider mass was, the MC was 194.4 grams, and our hook and our weight that we added to it was 14.8 grams, and that one was shown by the variable MW. So we put it into that formula and we got 0.6933078394. So we condensed that into two significant figures and got 0.69 meters per second squared as our theoretical acceleration over the final time. This is the position versus time graph. You can tell as it's going away from the sensor, it's going up. As it goes towards the sensor, it's going down. On the position versus time graph, we went ahead and stretched and focused in and created our velocity versus time graph. From there, we created 2 points at the beginning of our movement, or our third one, and then 2 other points towards the end. So as you can tell, the third movement's already going up. We have a point there, another point right afterwards. As it's decreasing, we have the first point and then the second point. Using those points, we used to find our initial velocity and to find our final velocity using the same formula that we had originally used in the previous lab. And then continuing after we got our position and our velocity versus time graph, we went and created our acceleration versus time graph. That way we could go ahead and compare everything all at once. And this is just a screenshot of the graphs that we created, or the graphs that were created from our original position versus time graph. So our first position was position 0.22 at the time 4.6 seconds. Our second position was 0.21 at the time of 4.7 seconds. And then our third position was 0.07 and at the time 5.20 seconds. And then our final position was 0.02 and our final time was 5.30 seconds. And so using the original position versus time graph, we plotted the 2 points at the start and of the third hill and then another 2 points at the end of the hill. We went ahead and plugged in our information into this table, and then we calculated our initial velocity was negative 0.1 meters per second, and our final velocity was 0.5 meters per second. So our first time was 4.60, and then our last time was 5.3 seconds. Following creating our graph and annotating it and then plugging all those values into our table previously, finding our velocities, we then went to our step 2, which was creating our third table, which was velocity values and acceleration number 2 or number 1. For our acceleration, the formula is final velocity minus the initial velocity divided by final time minus initial time. So for that one, originally it was the negative 0.5 minus the 0.1 divided by 5.3 minus 4.6, which was our time 4 minus our time 1. And we got the 0.57 meters per second squared. After calculating our first acceleration, we then went back to our graph, our original position versus time graph, and the velocity versus time graph that we had found, and picked our velocities 1 and 2, which were really our point 1 and our point 3. We could have also done our point 2 and our point 4, but we picked 1 and 3. So for our 1, our initial velocity was 0.05, and our time was 4.6. And then our second velocity was our third point, which was 0.45, and our time was 5.2 seconds. So our velocity change for the first part was 0.4, and our time change was 0.6. So getting our velocity and then putting into the formula for our acceleration, which again, final velocity minus initial velocity divided by the time, got us the 0.67 meters per second squared. And then finally, step 4, we created our table number 4, which was finding our acceleration 3. And then this is just a zoomed in version of our previous graphs. Again, the position, velocity, and then our acceleration graph. We just zoomed in following the prompts from the lab. We scaled our graph and we used the statistical icon to find the value's mean. And then we recorded that value in this table. So our acceleration 3 was 0.35. And again, it's that little pink highlighted version on our last bottom graph, which is the acceleration graph. And then now our step 5 of lab 3 was to compare the theoretical acceleration with each of the accelerations that we computed. We stated that the first two were found from our calculations. So our first one was found through the position versus time graph, and the positions, the points that we put, we found the velocity, and from that velocity, we created our first acceleration. Second acceleration was using the positions again, but more specifically, positions 1 and 3 to find our specific acceleration number 2. And then acceleration 3, our final acceleration, was one that was given to us by finding the mean from the graph that was made by the computer for the acceleration. So that
To conclude, this lab focused on investigating the acceleration of a glider pulled by a hanging mass and compared our measured accelerations to the theoretical value which we calculated and predicted by Newton's second law. We obtained 3 different experimental accelerations from the position versus time, velocity versus time, and acceleration versus time graphs that we obtained in Capstone. These values were compared to our theoretical acceleration, and from there we determined the percent error and evaluated the accuracy of our measurements. So going into the questions, should these percent errors be similar or not? So the aim for them is to be similar and towards the lower end, which indicates more accuracy. Where did this error come from? There's a number of reasons that errors can happen, some being real life factors like friction, air resistance, or sensor timing. Can or should this error be precisely zero? While you could get really close to zero, it's basically impossible since there's a variety of factors that could impact results. It shouldn't be exactly zero, but it could be relatively close. So set with your team members the threshold of this value to consider a good, regular, and bad experiment of this type. So for our experiment, we would consider it regular because the percent errors weren't too high, except for the acceleration versus time graph. If you could calculate acceleration again, which method would you choose? So we would choose the second method of calculating it from the velocity versus time graph since that yielded the lower percent error. So overall, this lab demonstrates how Newton's second law predicts motion and the various methods that we can use to analyze that motion. So the different methods gave us different results, which we went into the reasoning behind that. Thank you.